See. Okay, so today we're talking about how do we involve or how do we find limits if we're around vertical asymptotes, and also how do we evaluate limits if it's end behavior, if we're towards going towards horizontal asymptotes. Let's start with this here. Use the function f of x to answer the following. Identify all vertical asymptotes. So let's just go ahead and factor everything we see, and then we know our vertical asymptotes is going to be related to your factors in the denominator that don't cancel out. Okay, all right, so try that, see if you can factor and identify where the vertical asymptotes are. Okay, what you guys find? Where's our vertical asymptote? 3, yeah. Vertical asymptote is at x equals 3. Why not involving the x plus 4? Because it's a hole. It's a hole. Okay. So at holes, we know the limit does exist, but we know that at a vertical asymptote, the limit does not exist, right? X squared, yeah. Sorry. Yeah, sorry, x squared. So we know the limit doesn't exist at x equals 3, right? So we know that is true. So we can say that the limit as x approaches 3 of f of x does not exist. Okay. However, if we're asking for one-sided limits, these do exist because as we get closer and closer towards an asymptote, what's happening to the y value? It's either going where? Up to positive infinity or to negative infinity. Okay, so let me just show you what the graph looks like. Sorry, it's further up here. Let's go something like that. All right, now let's say you had the graph in front of you. What would the limit be as we approach 3 from the left side of 3? Yep, so that means we're picking a point to the left side of 3. And then we're just following the graph towards 3. And the y value is headed towards negative infinity. So we'll say negative infinity. Okay. What about approaching 3 from the right side of 3? Positive infinity, right? If I pick a point to the right of 3, and if I follow the graph up, it would lead me up to positive infinity. Okay. Now, this is easy to do if we have the graph in front of us, right? But let's say we did not have the graph in front of us. And all we know is that, okay, there's an asymptote at x equals 3, but how do we know which direction it's headed if we don't have the graph in front of us, and we don't want to have to graph every order pair to figure out where the graph is going? So what we're going to do is we'll take the reduced expression. We'll remove the x plus 4 because that's not going to impact us making our decision here. And I'm just going to do this. Limit as x approaches 3 from the left side of 3 of x minus 2 over x minus 3. we already know what the answer is from negative infinity. But let's say this was the problem given to you and you had to evaluate it from scratch. Okay. So let me walk you through that process. The first thing you do is you do direct substitution. Okay. Ignore the fact that it's a one-sided limit. Just plug in that x value. And what do we get? 1 over 0. So whenever you see a non-zero over 0, that is a visual reminder that you're dealing with a vertical asymptote. Okay, and you know that the limit doesn't exist. However, we can't say that the limit doesn't exist for this problem because if we're approaching an asymptote and if we're only asking for a one-sided limit, it's either positive or negative infinity. And the way that once you realize there's a vertical asymptote and that is a one-sided limit, we're going to do something that we can just plug in a numeric value and we know which direction it's headed. We're going to pick a decimal value that is relatively close to 3 from the left side of 3. So, I mean, we could choose 2 or choose 1, but sometimes we're not getting as good of a read off those numbers. If we choose a number like 2.9, then we're going to have a much easier time determining what's happening to the graph because we're assuming that we don't have the graph in front of us, okay? And we don't have a graphing calculator. So what we do is you're going to plug 2.9 in for x without a calculator. I know that feels intimidating or annoying because it's decimals, but all we care about is the sign, right? So we're going to do 2.9 minus 2 over 2.9 minus 3. All I care about is what the sign is. 2.9 minus 2, positive or negative? Positive. 2.9 minus 3, negative. What's positive or negative? Negative. So that's enough for me to know I'm headed towards an asymptote, and I'm just asking about the movement from the left side. And if I see that plus over minus, that's enough for me to know that I'm going down towards negative infinity. Okay. Number 3, let me just write the reduced expression, and let's do the limit as x approaches 3 from the right side of 3. Again, we're going to assume that we don't know anything about this expression. First things first, direct substitution. Okay. So when you do direct substitution, you're going to ignore the one-sided limit. All right, so we plug in 3. Again, what do we get? 1 over 0. So that is a sign that we know there's a vertical asymptote. We know our graph is doing one of a couple of things. It's either both going down, maybe both going up, or one going up, the other going down. We just don't know which variation it's going. So now we know that we're approaching an asymptote from the right side of the asymptote, and we know it's either positive or negative infinity, and we're assuming that we don't see the graph in front of us. So what decimal value can we choose from the right side of 3? 3.1. Okay, so choose 3.1. In for x, we get 3.1 minus 2 divided by 3.1 minus 3. Numerator, we get positive. Denominator, we get positive. Therefore, positive infinity. Okay, any questions so far? Now here's something that a trap that a lot of students fall into. The trap is that now that we have the idea in our head that, oh, if we see a decimal, I mean, if we see a plus or minus, it could be along an asymptote, and we got to test decimals. But sometimes the problem has no asymptotes at that x value and is still asking for a one-sided limit. So if that's the case, then just pretend like you're just finding the limit and you're only playing with decimals when you realize that there's a vertical asymptote. Okay. If there's a hole, ignore the asymptote. If it's a continuous function, sorry, if there's a hole, ignore the one-sided limit. If it's continuous function, you also ignore the one-sided limit. The one-sided limit, the decimal is only going to be activated when you realize that there is a vertical asymptote. And the only reason we're dealing with decimals is because we're trying to decide where the graph is headed, because we know it's one of two things. It's headed towards an asymptote, and we're trying to decide between plus or minus infinity. Okay. So let me change number 4 a little bit just to show you what I'm talking about. Okay, let's say I gave you this problem here. Limit as x approaches 3 from the right side of 3 of 1 minus x over x minus 4. Okay. First things first, what do we do? Plug in what? Just 3, right? Just 3. Okay, so 1 minus 3 over 3 minus 4. And what do we get? -2 over -1, which is 2. And that is our limit. That's a real number, so we stop. We don't do 3.1. We don't do anything like that, right? So I see students, they see that 3 with the plus, and they start instantly thinking, okay, I got to do decimals. And they start putting decimals in. You're only doing decimals if you realize after direct substitution that you're staring at a vertical asymptote. Okay? Because you know the limit doesn't exist, and it's asking for a one-sided limit. It's only asking for the behavior from one side or from the other side. So we got to be disciplined here. Don't let that one-sided limit throw you off. You're not going to touch decimals until something tells you to touch decimals. Okay. Let me do one more variation. Let me change this one as well. Limit as x approaches 1. From the left. Plus x minus 2. Yeah, over x minus 1. Okay. Limit as x approaches, again, I'm changing these problems here. I want to show you different variations. Limit as x approaches 1 from the left side of 1, x squared plus x minus 2 over x minus 1. Okay, first things first, what do we do? Yep, what do we plug in? Just 1, right? Don't get thrown off by the one-side limit. Don't think, oh, I'm going to do 0.9. There's nothing yet that tells us to do that. Okay, so plug 1 in. What do we get? 0 over 0. What does that tell you? There's a hole. Does limit exist? Yes. We have to go through factoring and reduce. What happens? Yep, x minus 1 cancels out. Reevaluate, we get. What do we get? Yep, and then 3. No decimals, right? If direct substitution gives you a real number, there's no decimals. If there's a hole in the graph, no decimals either, right? Because the limit exists. So it doesn't matter if we're coming from the left side or the right side, we're going to get an agreement of 3. Right? So decimals only if there is a vertical asymptote after direct substitution. Right? So that's why direct substitution is so important, because just by doing direct substitution, you know which category you're dealing with. Are you dealing with a real number? Are you dealing with a hole? Or are you dealing with a vertical asymptote? Right? So if you skip that first step of direct substitution, you're making an assumption, and sometimes that assumption is wrong, and then you may go down the wrong path. So your direct substitution is kind of like your anchor step. It gives you a direct line path to where the problem is going. The rest of these problems are just factoring and finding vertical asymptotes. I'm going to skip these problems, but are we okay here? All right, horizontal asymptotes. This is end behavior. So end behavior says, what is the y value approach as the x value approaches negative infinity and positive infinity? Does the graph approach a specific number, or is it growing without bound? So with horizontal asymptotes, we're looking to see, what is the behavior of the graph as we exit the graph from view, right? Is it headed towards a horizontal asymptote, or is the graph, maybe there is no horizontal asymptote and is just continuing to positive or negative infinity without bound? So you're going to see some problems that's going to be saying limit as x approaches infinity or limit as x approaches negative infinity. If you approach infinity, we don't do direct substitution. We have a different set of steps, which I think you're familiar with because you've done end behavior in the past. And if you see approaching infinity or negative infinity, you got to switch gears and you got to think, okay, I have a different set of rules, and my set of rules is comparing degrees. Okay. So if my numerator degree is less than my denominator degree, then my horizontal asymptote is 0, which is also going to match what the limit is. So for example, 3x squared minus 7 over 2x cubed plus 1. If you also think about it this way, if I plug in a really, really large number, if I keep increasing that value, which side is growing at a faster rate, my denominator or my numerator? Denominator. That x cubed is eventually going to overtake x squared, and this fraction is going to get what? Smaller and smaller and smaller, and therefore it's going to approach 0. Okay, so even if you feel like you're going to forget this rule, just go through it logically, right? What's happening to this fraction if I keep increasing the number? My denominator is getting larger faster than my numerator, and I know that eventually this value is going to get closer to 0. So my limit is 0, which also lines up with this idea of horizontal asymptote. If my numerator and denominator degree or have the same degree, then they're both going to be increasing at the same rate, and that rate is going to be just based off of the ratio of the coefficients. So if we're approaching infinity, and if my highest degree is degree 2, and my lowest degree, and my denominator also has that same degree, then I know that my limit is just the ratio of the coefficients, so just 5 over 2. And for example 3, I'm approaching infinity. I'm also comparing degrees, but now which degree is the higher one? Numerator. So that means my numerator is growing faster than my denominator, which means that my graph is growing without bound. If that's the case, there is no horizontal asymptote, but your limit is either going to be positive infinity or negative infinity. It's either one of those two options. And the way we decide between these two, an easy way to do it, is we choose a large number in the direction that we're headed. And an easy number for me to test if I'm going towards positive infinity is I just test 100. And again, this may feel intimidating or just feel annoying to do without a calculator, but you're just doing the same thing as before. You're just plugging in, and you just care. All you are worried about is what the sign is going to be. Because if the sign is positive, you know it's headed here. If the sign is negative, you know it's headed here. So if I plug 100 into the numerator, positive or negative? Denominator, also positive. So positive over positive is positive. So therefore, there is no horizontal asymptote, but my limit is positive infinity because my graph is doing something like this. It is just kind of rising without that. Okay. Couple of things that I want to point out is if my degree in the denominator is greater than my numerator, it doesn't matter if I'm headed to positive or negative infinity, my limit is always going to be 0. Okay. If my degrees are the same, and if I'm approaching positive or negative infinity, it is always just a ratio. Sometimes I see students get thrown off. They see limit approaching negative infinity, and they feel, oh, this negative infinity, maybe I got to do something different, and they end up changing the sign. So the sign, the direction of infinity doesn't matter if the degrees are the same or if the denominator is a higher degree. The only time your positive negative is going to make an impact is if my degree is higher in the numerator than the denominator. Then, depending on which direction you're headed, if I'm headed to the right, I'll choose to test 100. If I'm headed left, then I'll choose to test negative 100. Okay, let's try 4 through 9. Give you a moment to just try these problems, and then I will go through the answers with you. Okay, so try 4 through 9. And all these are under infinity, under this umbrella of infinity, so you know you're just comparing degrees, right? You're not plugging anything in. Okay, for number 4, my degree in the numerator is greater than my denominator. I'm approaching infinity. I'm comparing degrees. Numerator wins out. So I know that my fraction is getting larger and larger, but I don't know which direction. Is it headed towards positive or is it headed towards negativity? So to help confirm, I'm going to test a number in the direction that I'm headed. I'm headed right towards positivity. So I'll just test an easy large number like 100. And numerator gives me positive, denominator gives me positive. So I'm able to decide that I'm headed towards positive infinity. Number 5, again, my numerator is higher than my denominator. So again, it's either positive or negative infinity. This time I'm headed left. So I'm going to test negative 100 and see what sign I get. I get positive over a negative. So that's enough for me to say negative infinity. Number 6, my degrees are the same. So I'm just taking the ratio of the coefficients. 3 over negative 2 is negative 3/2. It doesn't matter that I'm going towards negative infinity. That's not going to change how I do my ratio. My ratio will be the same regardless if I'm headed towards positive or negative. There's only one asymptote. Okay? It's going to be the same on both sides. Number 7, just to highlight that there are no difference if my degrees are the same. If there's positive infinity, it's negative 3/2. If there's negative infinity, it's also negative 3/2. Number 8, My denominator is greater than my numerator. My fraction is getting smaller and smaller and smaller. So therefore headed towards 0. And number 9, my degree in the numerator is higher. So it's either positive or negative infinity. I'm headed towards negative infinity, so I'll test negative 100. And my numerator gives me negative, the denominator is positive, so negative 40. Any questions? Okay. I have 2 more topics that I want to run through. So that's going to be on page 29. Everybody okay with 28? Okay. Put a star next to this problem here, example 10. This is an exception to the rule. Okay, most graphs don't behave like this. So this is kind of like a very kind of like a strange exception. But the reason that I'm going over this is because we've seen this on the AP exam. So just know that this is more of an exception. The chances of this showing up on the exam is pretty low, but we've seen it before, so we want to go over it. So this is a very specific instance where the graph may have 2 separate horizontal asymptotes. This is not normal. Normally, your rational function is just going to show the same asymptote. It's not going to split on either side like this. But what gives it away is if I have a numerator, or if either my numerator or denominator is showing a radical. Okay. What is the degree of my numerator? 1. What's the degree of my denominator? Also 1. So the degrees are the same, but that radical is kind of making things a little bit strange. So that's why we are going to have horizontal asymptotes, because the degrees are the same, but that radical is kind of forcing things to change a little bit on both sides. Okay. So if the degrees are the same and if there's a radical on one side, then that's an indication, okay, we may be dealing with one of these strange graphs that have these split asymptotes. Okay. And if you know that there's a potential for split asymptotes, we're going to be looking for those asymptotes. Okay. So the way we find them is we do this. We do the limits as x approaches infinity of the expression that we see. And we know that the degrees are the same. We're just going to take the ratio of the coefficients. Okay. What's the coefficient of the numerator? 3. What's the ratio of the denominator? Sorry, the coefficient of the denominator. 2. It's 2. The square root of x squared makes it go down to x. Root 4 becomes 2. So we actually have 3/2. And so we have a horizontal asymptote. If we're headed to the right, we have a horizontal asymptote at y equals 3/2. And this is what the graph looks like. It's kind of flattening out around 3/2. Okay. All right, let's try this one. Limit as x approaches negative infinity. We're testing the other side as well, because we're expecting maybe something a little bit different here. Okay. Again, we do the ratio of the coefficients, right? Headed towards negative infinity. But numerator is still 3. Denominator is still root 4. But here's something that is strange, is that when we plug in a negative value into here, what am I going to get? Negative value. But if I plug negative value into here, what am I going to get? Positive. So that's why there's this they're not going to agree anymore. That square root is always going to protect this from being negative, and only this is turning negative. And that's what's causing this asymptote to switch sides. So that's why we're going to get y equals -3/2. So here's the short version. The short version is whenever you see degrees matching, but one side has a radical, you can just find the ratio of the coefficients, and you know there's going to be a plus and minus. That's it. We have horizontal asymptotes at y equals 3/2 and y equals -3/2. This is the only time you're going to have two different horizontal asymptotes within the same function, depending on which direction you're headed. Any questions? We'll have a lot of time to review next week. We'll have Monday and Tuesday to review. Wednesday, Thursday, I'm going to start the next unit, but we can still save a little bit of time to review. And you guys will still have a week to prepare for your test next Friday. Okay, so we are going to get a chance to put it all together. Part C, comparative growth rates. Families of functions grow at predictable rates in relation to each other if we approach infinity. So this only works if we're approaching infinity. So here's the basic relationship that we're going to see. Logarithms, so for instance, natural log of x is, if we're approaching positive infinity, it is growing. They can tell natural log of x is kind of inching along and it's growing at a very slow rate. Okay, radical functions like square root of x grows a little faster than natural log of x, but it's still relatively slow. Polynomials like x squared, x cubed, x to the fourth, we can see that it is rising at a faster rate than the previous ones. And finally, exponential function like 2 to the x, e to the x. If I have a variable in the exponent, my exponential function grows at the fastest rate. Right. So here's what's nice about this relationship. If I say the limit as x approaches infinity, if I have a slower function over a faster function, what's going to happen to my fraction? 0. My denominator is getting larger faster. That fraction is getting smaller and smaller. And eventually, we know the limit is going to go to 0. Okay. All right. What if I have a faster growing function over a slower growing function? Two options. It's either what? Positive or negative infinity. And then to decide between these two, we can just test what? 100. Yeah, you can test other numbers as well, but I like 100. It's just an easy, large number. You're never going to test negative 100 because this relationship only works if we're going to the right. Okay, right. Let's look at example 11. Limit as x approaches infinity, square root of 5,000x plus 1,000. What category, what family is this under? It's a square root or a radical. X squared is a what? Polynomial. Okay. Which side is growing faster? Polynomial. Therefore, this fraction is headed towards 0. Yep. Okay. Approaching infinity. What category can I put the numerator under? Logs. 2x. Okay, 2x. I would consider it algebraic. It kind of is not quite degree 2, but it is still rising faster than these two. So if you see 2x algebraic, I would still say it's polynomial. Okay, which side is growing faster? Therefore, 0. All right. Example 12. Numerator is exponential. Denominator is polynomial. Which side is growing faster? Exponential. So I know I'm down to two options, right? And what can I do? Plug in 100. So negative e to 200, is that positive or negative? Negative. And then 1,000 times 100 to the 4 plus 100 to the 5th, this is negative or positive is negative, so negative. All right, example 14. Numerator is a radical. Denominator is logs, which is growing faster. Radicals. So therefore, it's one of two options. I'll get 100. Numerator, I get negative. Denominator, I get, therefore, negative infinity. Okay, so this is easy as long as you know the order of the relationships. Okay. So just a real quick recap. I think this can get confusing. The previous limits can get confusing when things are all mixed together. But here's the big picture. If limit is approaching a real number, what do we do first? Direct substitution. Ignore the one-side limit. If there's a one-side limit, it may or may not impact you. Okay, so don't let the one-side limit throw you off. Always just plug in the integer value. And if I plug in the integer value, I'm either going to get one of three things. I'll get a real number, I'll get a 0 over 0, or I'll get a vertical asymptote. If I get a 0 over 0, I'll just go through my factoring steps, clean up. I know my answer is waiting for me. If I get a real number, then I stop. But if I get a vertical asymptote, then if you realize it's a one-side limit, then you play with decimals. Then you plug in 3.1 or 2.9. Okay, but that's the only time you do it. It's got to be a vertical asymptote after direct substitution, and it's got to be a one-side limit. And then if you're approaching positive or negative infinity, you got to switch gears completely. You got to compare degrees. Okay? So navigating between those types of problems all mixed together is what we need practice with. Okay, so we'll get plenty of practice for that next week. Okay, so your homework. Okay, page 27 to 30. I'll send out a reminder on Sunday since it's over the weekend. I'll be checking these pages. And then I'll give you guys a test review packet, and we'll start working through that on Monday. All right, thanks, everyone.
Oh, okay. No, I. So wasn't at one point when you guys did. I.